As the 1980s rolled around, changes were in the wind for the world of ride safety. It would be in this time that the ASTM F24 committee would be established. ASTM F24 was formed to focus on amusement ride safety as it pertains to their design and operation. These standards are voluntary, but since their introduction, they've become required by over 30 US states. Accordingly, almost all ride manufacturers soon began following these standards. ASTM breaks rides into 5 categories, with corresponding restraint design requirements depending on the predicted forces the ride will subject riders to. These categories range from no restraints for rides that have very little changes in acceleration, to redundant restraints that secure the rider in multiple ways when rides experience strong negative Gs. Restraints are broken into 5 different areas by ASTM based on the G-forces riders will experience on the ride. It's important to remember that G-forces are just a measure of acceleration, and so for simplicity, ASTM breaks the different axes riders will be exposed to G-forces into X, Y, and Z. X being forwards and backwards relative to a rider's eyes, Y being left and right relative to a rider's eyes, and Z being up and down relative to a rider's eyes. Area 1 restraints are the least restrictive and generally refers to no restraint at all. Think of a ride like a carousel. Going to the next level, Area 2 restraints may accommodate multiple riders or just one. They may have a final latching position that is fixed or variable relative to the rider, meaning they can lock in multiple positions or just one. The rider or the operator may be able to unlock it. It can be manually or automatically opened or closed, and redundancy is not required. Some examples of restraints like this are those on old Aero mine trains and the locking bar on scrambler type attractions. Area 3 steps it up a little bit, with most of the same requirements as Area 2, except that these restraints must be capable of locking in multiple positions relative to the rider, and that the operators must check that the restraints are secured in some way. Think of the large adjustable lap bar on Big Thunder Mountain Railroad, for example. Area 4 restraints step things up further by requiring one restraint be provided for each individual rider, requiring that restraints must be automatically locked, that only the operator have the ability to unlock the restraint, and that redundancy is now required. This redundancy can be achieved through multiple independent systems in the restraint system, such as 2 independent locking pins, or by a separate device like a seatbelt. Think of older B&M looping coasters with simple over-the-shoulder restraints like Raptor at Cedar Point. Area 5 is reserved for the most intense rides. It has all the requirements of Area 4, but adds a requirement for some kind of external way of verifying that a restraint is secured. This is usually accomplished through a seat sensor. This is a magnetic sensor that verifies every restraint is in the correct position before it allows the ride to start. Area 5 restraints also require 2 restraints or 1 fail-safe restraint. An example of rides with 2 restraints are top spins, which use an over-the-shoulder restraint as well as a lap bar. Most Area 5 restraints opt for having 1 fail-safe restraint instead. Some examples of this are the restraints used on RMC coasters, which use 2 independent hydraulic systems to secure each lap bar. The area a ride's restraints must comply with is determined by this graph. Ride manufacturers must calculate the G-forces their rides will subject riders to and plot them on this graph to determine the minimum qualities of their restraints. Let's do a quick example with the Zamperla Skater coaster. Plugging in the recorded G-force data from the ride recorded by G-Force Productions, we can see that this ride falls under Class 2. Examining the ride, we see that it uses 1 lap bar for 6 riders that can lock in multiple positions and is not redundant. This makes it a Class 3 restraint, making it more compliant than it needs to be. Now let's examine G-force limits. These are hard maximums placed on the G-forces rides can exert on riders in specific directions. The limits are slightly increased if riders are in a prone position. Feel free to pause to examine these limits in more detail. Let's examine the rules on transitioning from one direction to another. ASTM defines sustained time of riders experiencing a certain amount of G-forces to be any acceleration lasting longer than 200 milliseconds. When riders are exposed to sustained high negative or positive accelerations, ASTM requires there be at least 200 milliseconds between these forces. The change in G-force is limited to no more than 15 G per second. This means that a ride cannot go directly from keeping riders weightless to throwing them into their seats. Instead, there must be a transition time of 200 milliseconds or more. Exceptions are made for g-forces that are well within the limits, and those that are very brief, lasting less than 200 milliseconds. This flowchart by ASTM explains how this rule is applied. Know that this rule applies to g-force changes on the x, y, and z axis, but is particularly focused on the z axis, that meaning up and down relative to the rider. Let's take another example. Skyrush at Hershey Park is known for its fast transitions from negative to positive z g-forces, but is it ASTM compliant? Here is a graph of the g-force data provided by g-force production starting from the first drop on the coaster. Mind you that this data is not extremely accurate as it was only measured on a smartwatch, but we can clearly see a well-defined transition between peak g-forces in both the positive z and negative z directions. Here, entering the third negative z moment on the ride, we can see a textbook 200 millisecond transition from around +3 to 0g. Entering the fourth negative z moment, we can see a very fast transition from positive z forces to negative. Here we can see the designers opted to keep forces lower temporarily during the transition time before riders experience the stronger forces later on in the element. So yes, even a ride as intense as Skyrush is ASTM compliant, and its designers likely worked hard to ensure that it was compliant. The oldest and most simple restraint type, the latching restraint. These restraints can only be set in two positions, opened and closed. They use a spring-loaded bar under the train or ride unit to latch the restraining device, usually a lap bar, in place. To change from open to closed, these restraints usually use a foot pedal that an operator must physically press. Due to this restraint system's design, it has no preference between being opened or closed, meaning that these restraints can come open during a ride cycle relatively easily when compared to the others we'll talk about in a moment. Due to this design, these restraints are generally not used very frequently anymore and remain on only very tame and old rides. Rides with this restraint type do have some mechanisms in place to ensure that restraints are in the proper position though. One of these is a pedal check sensor. As restraint release pedals will be in a different height when restraints are closed versus being open, a sensor may be added to a ride with these restraints that magnetically detects when a pedal is in the closed position. If this sensor does not detect a pedal in the correct position, it will stop the dispatching train. The next type of restraint was designed to replace the single position latching restraint, the multi-position ratcheting restraint. This design works off the simple principle of a ratchet, a mechanical device that can move freely in one direction but is unable to move in the opposite direction. The simplest of these designs use a toothed rod with locking pins, usually at least two for redundancy. These pins slide into the rod, preventing it from moving down but allowing it to move up. This in turn allows the rider to lower their restraint at any time, but it does not allow the restraint to become open until an outside entity interacts with the system. The locking pins are spring-loaded into position, requiring force to remove them from the locked position. In this way, the ratchet design defaults to the locked position, making it considerably safer than the latching restraint. More advanced version of this design, such as those found on B&M roller coasters, use a drum-like ratchet with several hammer pins. This restraint design does suffer from one flaw that has resulted in them slowly fading away, and that is that they're only able to lock in a predetermined number of positions. On B&M rides, for example, they have 8 different settings. If a rider does not fit one of these settings perfectly, they will have some play in their restraint. This causes some riders to be concerned. However, this is how the restraints are designed. These types of restraints can also experience a problem known as a slipped ratchet. A slipped ratchet occurs when the locking pins of the restraint don't fully engage due to being right at the point of engagement. Then, usually after the ride is started, the rider will put some force on their restraint that causes the device to pop up into the next highest setting, making it feel like the restraint has temporarily released. This is more common when the ratchet device gets worn or when there is debris in the device. This can be scary, and on some rides where the highest ratchet position is an allowed position for the restraint to be in, it can result in the restraint releasing entirely, though it will lock again if pushed down. This was the case for the highly publicized incident on the Desert Storm roller coaster at Castles and Coasters. In this case, a lap bar secured by a ratchet system slipped from the top ratchet, which allowed the restraint to be completely open. In this case, the rider chose to leave the moving train rather than to pull the lap bar back down, where it could have been resecured. Ratcheting style restraints are unlocked by physical force. On most rides, this takes the form of a bar that raises and lowers in the station area, pushing against an assembly that pulls back the locking pins against the force of the spring. When this bar is removed, the restraints default back to locked. These types of restraints can only be unlocked this way in the station area. If restraints need to be unlocked outside of the station, this can only be accomplished by constantly applying pressure with a device such as a pedal attached to part of the ride unit or a specialized tool. If pressure stops being applied, the restraints will default back to being locked. The final type of restraints are hydraulic restraints. This design works by having a hydraulic solenoid that uses hydraulic pressure to remain in the same position. This is generally accomplished through a closed-loop system that typically, but not always, includes a check valve, which allows fluid to flow in one direction but not the other, allowing restraints to lower but not raise during the ride. Some versions do not feature check valves and thus remain in the same position for the entire ride. These restraints can be unlocked with an electrical signal. On most rides, this electrical signal is sent by a contactor that raises under the ride unit and sends an electrical signal to unlock the restraints. This then opens a valve in the solenoid, allowing the restraints to move. Hydraulic restraints often feel heavy as when you move them, you're moving the hydraulic fluid through the system. They also make no noise. These restraints may be set up with multiple solenoids in order to have redundancy, or they may use multiple to reduce the wear and tear on individual solenoids. The only way for this type of restraint to be unlocked outside of the station area is with an electrical signal in most cases. This means that if the hydraulic restraints need to be unlocked outside of the station area, a battery pack is often used and hooked up directly to them. In other cases, a screw may be accessible that can manually release the pressure in the system. These types of restraints often feature seat sensors. This is a system that communicates with the ride's control system the secured status of each individual restraint. These are found on other restraint types too, but are most common on hydraulic systems as there's already electricity being supplied to the train. Seat sensors consist of a magnetic proximity sensor mounted to a part of each individual restraint. When the restraint is lowered to an allowed position, the sensor will send a signal to the ride's control system, telling it that the individual seat is safe and ready for dispatch. This is intended as an extra layer of safety on top of systems already in place. On new high-thrill rides, it's actually required to be a part of their design in areas that abide by ASTM standards. All of these restraint systems can be connected to any number of different restraint devices, such as lap bars or shoulder harnesses. These vary from ride to ride and manufacturer to manufacturer. Ratcheting restraints work by having a mechanical ratchet that interlocks with several spring-loaded locking pins. The design of the ratchet allows the restraint to move further down into a more closed position, but it will not allow it to move into a more open position. This is due to the shape of the ratchet device, as when the pins are engaged, they will physically block the ratchet device from moving. These restraints are unlocked by an outside force, such as a mechanical bar or other system under the ride unit, moving the pins out of engagement with the ratchet device. These restraints can only lock in a fixed number of positions due to their design. These restraints are also known for making the iconic click sound when lowered. Another major design of ride restraint is the hydraulic restraint. These work by having a hydraulic solenoid with electrically controlled gates that allow fluid to flow in all directions when unlocked, but only allow it to flow in one direction when locked. These are actuated by an electrical signal, and when unpowered, they default to a locked state. If you would like to learn more about how ride restraints work, check out this video. The situations where this experience is reported to have occurred are coming from rides with ratcheting restraints. As we discussed, these restraints have a set number of positions they can lock into, determined by the location of the grooves on the ratchet device relative to the locking pins. This, in effect, means that many rides with these restraints only have between 6 to 12 different possible positions for their restraints. This means that if a rider's size falls between these settings, there will be some small amount of movement on the restraint. This is due to the locking pins not engaging with the lower ratchet and there being some room between the lower ratchet and the higher one. This can result in several inches of play in the restraints of some rides. This is very normal and expected behavior with this restraint type. but it does not explain why sometimes these restraints can seem to suddenly jump up a setting, making riders understandably think that their restraint temporarily unlocked. This situation can instead be explained by looking closely at the design of some ratcheting restraints. If a ratchet is lowered just past the peak of one ratchet, the pin may be partially engaged with the lower setting. When enough force is applied to the restraint, usually by ride forces, the pin may slip up to a higher setting. When this happens, the restraint pins remain locked, the device was simply never fully locked into that lower setting. This problem can become more prevalent when the restraint ratchets have debris inside of them or are not well lubricated. Regardless, when this occurs, it can result in a rider's restraint moving up several inches suddenly. This can understandably be scary, especially if you do not know what's going on. Hopefully this video helps explain that background so you are prepared if you ever experience this. Just remember that if the restraint is locked in that higher setting, the restraint never unlocked. Instead, it simply slipped a ratchet. It's also worth noting that this is most prone to occurring when ratcheting style restraints are adjusted to be really tight on a rider. Ratcheting restraints are making a comeback in the industry, and the newest designs are far less prone to this problem. For example, the Infinite Restraint from Infinite Restraint Systems is a ratchet type device with exponentially more locking positions than a traditional device, and it features 4 locking pins. This results in slipped ratchets being less common, as well as the effects of them being much less noticeable, as the distance between locking points is much smaller. Regardless, this is still something to be aware of, and while it's not unsafe, it can still be very startling. Hopefully, if it ever happens to you or someone you know, you will now be able to explain what happened. If you'd like to learn more, check out my other videos on ride safety and design. As always, thanks for watching, and we'll see you next time.